the SYMBIOTIK project, to the theoretical neurobiology group. So the idea of this presentation, as you can see here in this introduction, is to first show you a bit of the project overview, how is the idea, what are the goals of this project, to then move on to our experimental task, what we have performed, the experiment that we performed in the last couple of months, and then go into the results that we already obtained. I'm going to mention briefly the results to go to the most interesting part about the discussion, the interpretation, and the next steps. But I'm going to present you about behavioral measurements results. I'm going to include some analysis of heart rate and electrodermal activity. Then I'm going to move on to mention some results about the eye tracking to wrap up with the EEG analysis and results. The idea of this, the presentation shouldn't be lasting more than half an hour. So the idea is to introduce you in the project, show you the main results, to then go to the main point of the presentation, which will be the next steps of our project, our challenges, so we can discuss and brainstorm about the future steps on how to approach the challenges we're having now. Of course, if you have any question, yes.
Sebastian, I apologize if I may jump in and say a few things before you start the presentation. I was just planning to, first of all, I'd like to thank Carl. He has been extremely generous to give us the opportunity to present in your standing meeting group. This is of tremendous help to us because this particular project is a Pathfinder project. It's one of those line of projects where we are expected to carry out basic science, but with a goal, a long-term goal of a long-term vision of reaching a higher TRL level. And we are a small consortium, relatively small consortium of 4 partners. I believe today with us is Professor Luis Leiva from the University of Luxembourg, who is the project coordinator. We have also his colleagues, I think Saravana, from what I can tell from the screen, sorry if I'm missing out anyone. And also from our side, Telefonica, Sebastian will be presenting today, Angela, and there are 2 more partners maybe not present today. Basically what we expect to achieve from this session, beyond what Sebastian described very clearly, is to have a discussion with you who are world-renowned experts on neuroscience, and we are very positive that you'll give us great feedback that will help us steer us in the right direction. What we expect to achieve is, in some cases, confirm, validate certain choices we made to date, and in other cases, when you feel like there are things we should consider doing differently in the next steps, to have that feedback from you. Pathfinder projects are high risk, high gain, and that high risk is not just a fancy word, it's real. And within those 4 years, we really need to work hard to deliver certain objectives and goals we have committed to. So with that, I'm going to wrap up and let Sebastian take you through this journey we had so far with its ups and downs. And what we really hope is not to give you a very technical presentation and baffle you with technical jargon, rather explain really the journey and hear from you what you think and give us your honest feedback and help us derive strategies for tackling the coming challenges that we have ahead of us. So I'm gonna stop here, and then again, Carl, we haven't met in person yet, but I feel like I kind of know you from and I'm really grateful for this opportunity. So again, thanks to everyone in your group for attending this.
Thank you for presenting, and looking forward to hearing about your journey so far. Thank you.
Thank you, Ioannis, for the introduction. Yeah, I skipped that, so I apologize. So as I was saying, the idea here is to show you around our project goals, our main results, and our next steps. So the idea of this project is born as we are all familiar with the exposition to screens. We are working with cell phones, with computers, with TV, and in daily basis, we're exposed to multiple screens and multiple amount of information at the same time. This exposure to prolonged time to a lot of information can lead to information overload, which can cause fatigue, and in the worst scenario, maybe burnout syndromes. And the idea of this is that we can tackle this problem by many different theories. One of them is the cognitive fit theory, which states that if there's a correspondence, if there's an alignment between the task to be performed and the information presented, then this could lead to a superior performance. Going to a practical example, as you can have here in the slides, a clinical room, a doctor with a patient, and you have many screens informing the state of the patient. If these screens inform valuable information about the state of the patient, then the doctor could have a clear understanding of the situation, can make a rapid assessment, and take decisive actions in favor of the health of the patient. Of course, it's not it's important to relevant that say that in these cases, like in the hospital, these clear and decisive actions could lead to different actions in the life and death situations that could help enhance the life quality and the life expectancy of the patients. But this could apply to many different fields. And the idea of this is that in these cases, the doctor in this example is a passive observer of the screens of the information that display the state of the patient. What we propose here in this project is a bio-inspired feedback loop to transform this user, this agent, this doctor in this case, from a passive observer to an implicit architect. And the way to do that is by introducing adaptive dashboards, in which the dashboard that the user, or in this case the doctor, is perceiving, that is seeing in the screens, adapt and interact with the person that is using it in real time. So this is derived from a framework called information visualization. Here for clarification is the InfoVis enhancement. And what we propose here in this project in SYMBIOTIK is the integration between a wide diverse of modalities, what we call a multimodal integration. And as I mentioned before, we collect data from the participants in many different types, not only the behavioral responses, reaction time and accuracy in any task, but also we measure the heart rate, electronic activity, eye tracking data, and EEG. The idea of all of this is to create a cognitive state of each participant, of each person, and with this cognitive state, with this information, we can use this data to enhance the information visualization, to emphasize in the moments that we want, and to diminish the details that are not relevant for the responding or for the performing of a task. Now, this application could be used in many different environments, but most of them, the idea is to create a human-centric perception analysis for not only situation, but also time-sensitive tasks. So if we can have this perception analysis, what we can do is to minimize the amount of thinking that goes into the reading, the interpreting, the processing, and increase the efficiency by making a priority the more relevant parts of a dashboard, to show it, to emphasize, and to make it clear what is the most important that should spend more time and not lose time in details that could slow down the process. Another way to approach this, another way to apply this in the real life environment is the training of novice individuals, the novice participants or users into experts. So if you have any kind of work, any kind of project in which you have many screens, a lot of information, a lot of parallel processing, what you can do is to train these participants to have a transition. So whenever there's a change, an updated environment, it doesn't need to learn everything again, but the person is already an expert that can perform faster and not lose time in these adaptations. And all of this is inspired in biology, as we are familiar, but just to be on the same page, with the concept of symbiosis come from the interaction between two different species. Two species can interact in many different ways, as you can see here. They can harm each other by competition. They can have no effect in the neutralism, but what we will focus here is in this mutualism, in this benefit. So by the benefit between two species, in this case, the human and the computer, or the user and the environment, what we can achieve is this symbiosis in which both help each other. So our proposal is to have an AI-driven awareness framework to create a symbiotic, self-adaptive InfoVis system. Having explained the project goal and what's our background of our project, I'm going to move on to the task that we perform in our labs. So here I'm showing you that we perform the task for 30 participants for this specific experiment, in which we record not only EEG, which is the main graph that you can see there, but also we have the behavioral responses, the heart rate, electronic activity, and eye tracking, as you can see in the bottom right. And in this task, consisting of multiple trials, what happens is that the person, of course, starts with a fixation cross in each of the trials to fixate the look in the center of the screen, followed by a question. So what you have is a person having a question that you can to read, and then afterwards, after reading the question, having a graph that will help them to respond the question. So the idea here is that we can have and assess different levels of magnitude of the effect by manipulating these conditions of how are the questions and how are the graphs. After responding, the person has a rest and then continue to the next trial and so on and so on. And I was saying that we can manipulate the conditions of the experiment to have different profiles of the cognitive load or the mental workload of the participants, or the mental state in this case. For example, we can manipulate the question complexity, as I mentioned before. You can have low complexity questions or easier questions, or high complexity questions, harder questions. But also we can manipulate the graph complexity. In this case, we can have low dimensionality graph, so low complexity graph in which you have 3 nodes, for example, or harder or high complexity nodes in which you have 6 nodes, for example. And this leaves us with a clear profile that we can disentangle that whichever response, both behavioral and physiological, occur from the participant in the low conditions is what we expect to have this, and in the hard or the difficult conditions is the one that you can see there in red as the most complicated scenario. But of course, what we want is not only to distinguish the profile to classify the different states of the participant, but actually to help them, to enhance them by giving them tools to navigate faster and more efficient the graphs. So what we'll introduce here, from the basis of the visual primitives, is some adaptations to try to modify these graphs. As you can see here as an example, a non-adaptive graph, all the information is displayed with any hint, just text display in the graph. But you can start introducing some visual primitives adaptations to make it simpler to navigate it. One example is if you just color code the gender of the participant. So instead of having an M or an F inside of the node, you just color code it saying that pink is going to be female and blue is going to be male. So it's easier to navigate and it's more salient, the feature of the gender. Other adaptations could be to have the shape of the node. For example, in our case, it's a fake criminal network. So we have if the person is currently in prison or not. By the shape of the square, you can know that the person is or not without having to read the content of the node. Other adaptations will be the size. So the more number of arrests the person has, the higher the size of the node. And also you can manipulate not only the nodes, but the edges. For example, by changing the color of the edges, in this case, to match or to indicate that they have matching birthplace, or the size of the edge to indicate the strength or the robustness of the relation. All of this leads to have a non-adaptive version of the graph, which has no information that is not displayed by text, to a fully adapted version that actually with these visual adaptations help the user to navigate not only more faster, but also more efficient to respond more accurate to the questions that are proposed in the task. So having explained our paradigm about the condition has different complexity of the question, complexity of the stimuli load and the adaptations, I'm going to move on to the results. So as I mentioned before, I'm going to go quickly through the results to not overwhelm you with the technical parts. If there's any doubt, we can, of course, come back afterwards and check for the details of what we have applied. So as a reference for all the figures in this presentation, always the darker color will be the harder or the more difficult conditions. The lighter the color will be the easier or the simpler conditions. So by checking the behavioral response, the easier way to do it is by measuring reaction time, how much time it takes to respond the correct questions. The participants, and as you can see here, the reaction time is significantly higher for the harder or the difficult questions compared to the easier questions that you have here. And also what we perform just to have a quality check is a simple classifier, an SVM, linear kernel, 80% training, 20% test, kind of default for the literature. And what we can see is in all the participants, I just show a subset to not overwhelm you with the amount of data, that in all of them, the performance of the classifier is above chance. So this result is replicated not only in the question complexity, but also on the stimuli load. So when you have more stimuli in the screen, 6 nodes against 3 nodes, the reaction time is higher. And also is perceived when you include our visual adaptations. What does it mean? In the left, you can see the non-adaptive conditions or trials in which we don't help the participants at all. It's just information displayed in text. And you can see that the reaction time is higher. When you introduce one adaptation, one at a time, the reaction time goes lower, but it goes even lower when you introduce all the adaptations together, as I mentioned before, the color, the shape, the size, etc. And something to clarify here, because if you want to help the person with modifying the environment to make an adaptive environment to help navigate better, it's not possible or it's not convenient to change too many things at the same time. It could be overwhelming the change and it could be difficult to follow if many things change at the same time. So what we did is to rank these adaptations so we know which of them is helping more individually. So what you can see here is each of the adaptations that I mentioned before, and in the x-axis you have the reaction time, so how much time it takes for the participant to respond to the question. And of course, the lower the reaction time, the better the performance. And we can see here that, for example, the color of the node seems to be the most informative feature. So if you want to help the participant to respond faster, the first thing to try would be to change or to add the color of the nodes. With this idea, we can have a hierarchy of these individual adaptations to modify in our next steps. And this also could be observed, as you can see here, the three top features are regarding to the nodes. The edges are the one having less influence, less impact in the performance of the participants. And if you go to the accuracy of the trials, the same pattern emerge in which the nodes seems to be the one contributing more. In this case, higher accuracy represents a better performance. And again, the nodes modification seems to be the one impacting more. So for our next steps in which we will start modifying the environment, we know which one to start and which one to introduce later in the sequential steps. Moving on to the next results. So I mentioned the behavioral results. I'm going to go now for the heart rate, as you can see here, explained by the PPG. What we know is that when a person is perceiving a stimuli that creates certain level of stress, the response is not only cognitive, as we can see afterwards in the same presentation, but also with some biological responses as an increased heart rate and sudation that can be measured by certain devices, certain electrodes, as you can see in the bottom left of the screen. This is the device that we use, including a LED light and a photodetector that actually will measure how much blood is flowing through the finger by seeing how much light is passing through the skin. So what we observe here, in the same way consistently to the behavioral results, is that we compare the question complexity, the harder scenarios with the simpler scenarios, the heart rate is higher for the more complicated environments. The same effect is visible when we compare with stimuli load, so amount of node in the screen, and also when you introduce the visual adaptations. As I mentioned before, I won't spend much time in this because I don't think it's the main purpose of this call. I would prefer to focus our time in the discussion and the next steps, but if there's doubt, we can always come back. And something that we have to take in consideration when we include these physiological measurements of heart rate and electrical activity is that there's a delay in the response. Maybe you are all familiar with this, but when you have a task, as you can perform here, let's say that you have this graph paradigm of question and responding with a graph, there's a perception of the system, autonomic response that goes to the sweat glands, and this response takes a few seconds to see an effect. So it's not immediate that you can see the consequence of the activity of the different type of conditions, but also what you can see is that there's a typical pattern of response in the human body. After seeing the stimulus, there is a certain time lag for afterwards going to an increase that takes around 3 to 4 seconds, and then reaching to the peak of activity for afterwards having a recovery phase before the next trial. Why do I specify this, especially in the EDA responses? Because when I present the results, and again, I remind you that the darker color is the more difficult scenarios, the lighter color is the simpler ones. If you check the first 3 seconds after the response, after having the response of the participant, you see that the effect is not clear, it's not evident, but once you compare after this time pass, so if you let the lag pass and the increase happens and the peak, you can see that the difference emerge and the harder condition elicitates a higher value of electrodermal activity. The same occurs with the stimuli load. In the first 3 seconds, there is no effect. After the fourth, start emerging, and the same happens with the visual adaptations that I'm not going to go into details. Okay, Moving on, I would like to spend a bit more time in these two last metrics that are the eye tracking and the EEG because they're more robust and they're more complex signals. As you might be all familiar, the eye tracking is a really rich metric in which you can not only quantify the fixation, so how much time it spent the person in specific points between the gaze, how much is the gaze focused on a specific area. You can not only see the amount of fixation, but also you can see the total time of the fixation, how much time it spends in each of the fixations. So to simplify our results, to not show you everything we have performed, I'm going to just focus on these two metrics, the amount of fixations and the fixation time, to have two indicators, two proxies to cognitive load. So as we mentioned before, I'm going to compare through the three different comparisons. In question complexity, you can see here how the high complexity trials have more time of fixation, have more time of in the stimuli load, also with the amount of fixations, and the same pattern also emerges when you compare the visual adaptations. Okay, and now moving to maybe the richest metric that we obtain here, which is the EEG analysis. And just to have a brief overview of what we have done for the pre-processing, principal results, and principal analysis, what we did is to first obtain the data, the raw data. We apply a simple filter, a bandpass filter, including a notch filter to get rid of the electrical current. We detect the bad channel as to try to not let influence in our signals. We perform an independent component analysis, and we interpolate the before mentioned bad channels. And I mention all of this because we can use this channel detection and this ICA to actually have a quality assessment of our data. As we rely on a 32 channels gel-based EEG, what we can see here is that the average for the bad channels that we discard per participant is around 1 or 2 channels, which is a quite good indicator of quality signal, quality assessment. But also we can see how many components we discard for each of the participants to indicate that there wasn't much noise, much interference, much independent artifacts present in the signal when we acquire it. Having said that, our analysis will be based on the famous ERP, even relay potentials, that you're all familiar with, but just to be on the same page, what we did is to take the raw signal, pre-process it, and then average across conditions. So when you do the average of the signal, what you obtain is 1 ERP per condition to compare and see the result that you want to see by comparing different levels of different categories of your task. Okay, now moving to the results. When you study what is the phenomena or compare between the conditions, one thing that you can do is the famous frequency analysis through a fast Fourier transform to separate in different frequency bands. As you're all familiar with this concept, just as to illustrate this point, we can just visualize a time frequency analysis, really rough, just for one example electrode, as we can already see that there's a difference mostly in the alpha frequency band and in the theta frequency band. But you can go more in details to see statistically where is the difference for phenomena related to these frequency bands. And some of them that we try to replicate because they're common in the literature that we are inspecting is, for example, the alpha symmetry. The alpha symmetry, which the name is kind of intuitive, what we contain is the power of the electrode in the front, the F3 and F4 in this case. We compare how asymmetrical was the signals, and we see if this is an indication of the mental workload of the task. And as before, as I mentioned, the darker color will indicate the harder condition. And as you can see here, the harder or the more difficult conditions show a higher alpha symmetry, showing that it could be used as a biomarker or as a metric to make the profile, the cognitive profile of the participants while doing the task. Another analysis that we can perform by profiting from the frequency analysis is the theta alpha ratio, in which we divide the theta power band divided by the alpha power. And again, I'm going to just show as an example to illustrate our point. We can go in detail for the most extensive results. But if you have an example of this FZ electrode, you can see that the theta alpha ratio is higher for the more difficult or the harder conditions compared to the simpler or easier conditions. And lastly, some metric that we need to use to compare with most of the papers that are in the field is basically calculating the entropy of the signal to have a sense of the regularity of the signal, to see how predictable sequences are occurring in our data. So we just choose two of the most used ones that is in the papers, which is the approximate entropy. And as you can see here, the results are consistent across the study, being the harder or the more difficult scenarios, the one with the higher entropy. We can also locate, I'm not going to go into details, but we can locate where is this phenomena happening and how you can expect also topologically this phenomena. And as a control, we also calculated the sample entropy, which is a bit more sensitive, that is more reliable for shorter data sequences and is less sensitive to data length, data approximate entropy. And this again shows the same pattern, the same significant trend when the harder or the more difficult conditions show a higher entropy. Having explained a bit shallowish and bit fast our results, let's go on to the next steps, as I mentioned before in the introduction. So everything I have shown now is by making a task, comparing different complexity of the graphs, as I mentioned in the task presentation. Our idea now is to replicate all these phenomena if we can do the profile of the cognitive state, but in other visualizations, in distribution plots, in time series, and so on, in idea to say that we can actually see the same effect in many different environments. Why is the reason of this? Because afterwards, what we want to achieve is to calculate or to assess the novice to expert transition. So if you have an expert condition in which you have different visualizations combined, in which the information is provided in different ways, as is more performed in daily based tasks or in most of the routine jobs. So the idea here is that you can learn how to navigate the different visualizations, the different environments, by combining and weighting different features of different stimulations. And the whole goal of this, I'm going to explain it in this slide, don't worry, I'm not going to go through the whole graph, it's just to illustrate the point. So we mentioned that we will explore different visualizations, as I mentioned before, graph, time series, distribution charts. I mentioned that we will collect, and that we have already collected for the graphs, many cross-modal sensory data, including heart rate, EEG, and eye tracking. An idea of all of this is to train to use a multi-objective deep reinforcement learning framework. What is the goal of this? As you can see here better in this figure, is to estimate, to define an environment, as you can see here in the bottom left box, in which you have an environment and a measure that we take, for example, here the EEG signal of the participant, then to define a state based on this information, to train the reinforcement learning model, to have these adaptation strategies that create this bio-inspired feedback loop to make this constant adaptation to the participant based on the state of the participant at that particular moment. Having said that, having explained our results and our main next steps, I'm going to move on to the challenges, and I'm going to try to go one by one and leaving the space to discuss with you. I'm going to also leave the room for Ioannis and Luis as coordinator of the project to frame the questions that they feel more appropriate for this point. The first challenge that we face and we are tackling now is about the scaling of the data. So the idea is, if we want to train a reinforcement learning module, how we can obtain enough data to train algorithms that require millions of data points, when our task, our experiments, we're talking about hundreds or thousands of data points. So our proposal that we are working now is to basically integrate the data that we obtain by including some padding, some defining features. So if we have our profile of how it will look, the reduced mental workload signal, the enhanced or the increased high mental workload signal, and we have some noise or padding to connect, we can create this series of data that, by integrating the different information, create longer strings of signal. So I leave the room for Ioannis and Luis if you want to add something, and if not, I open the room for discussion on how to tackle on this challenge.
Yeah, if I may add, I think Sebastian did a quite good description of the problem. I don't think there's much to add other than what he said, that the main challenge here is training an agent, an RL agent, to tackle this decision-making process of what kind of adaptations to apply at what time. And one practical challenge is the data sparsity. These kind of experiments are hardly scalable, and we've been looking into ways where we can synthesize new data or use existing open access data if they fit, the setup that we're looking into. But we were wondering if perhaps we could use the single trial data that we collected, which has, to some extent, some kind of it has internal validity and to some extent ecological validity, and combine these to create longer sequences, which would be possibly a way to train and fine-tune these models to some extent. Luis, I think you wanted to share something.
Yes, thank you. So the problem is that we don't have ground truth data for adaptations that have never been seen by the model. So let's say we start with some, I don't know, here we see some kind of baseline plots, and then you can take some previous trials and try to derive some adaptation. But if the produced adaptation is something completely new that nobody in the study saw before, then we have no idea what will be the behavioral responses for that particular adaptation. And that's why we need to either recombine or synthesize the existing data that we have. Otherwise, we are missing this ground truth, and we would like to hear from you what kind of ways of generating this feedback, or what would be a sensible way of producing some artificial data that is not too artificial, let's say, something that is as human-like as possible in order to tackle this problem.
Thank you. Yeah, I think this meeting is going to be a bit different. We usually go to the Q&A session and so on, but I feel here is going to be more like a general discussion. I have a question which is not related to this last thing about scaling the data, but how do you have different cross-model data, right? You mentioned before. How do you exactly combine those kind of cross-model data? Because it doesn't seem like very trivial thing to do, because you can have I don't know if you do that in sort of latent space in which you can combine, predict one latent space from one modality from the other, or just everything is packed into the same one. It feels like very non-trivial thing to do. So I'm curious how what ideas do you have based on that?
Yeah, I don't know if Ioannis or Luis want to jump in, or should I answer?
Please go ahead.
Okay, perfect. Yeah, thank you for the question, Miguel. So this was actually a question that will come afterwards, but we can discuss it now.
Okay.
The idea of this exactly is to integrate this modality in the reinforcement learning module, in which we can have just features provided by our physiological data. One way will be to go for a latent space in which we can integrate, but I think an easier approach will be if we summarize the data and create a profile for each of the measurements, and then combine these features, in which we see how consistent or not are, to see how reliable is the state assessment of the participant. So by having a profile of each of the metrics and see how consistent they are between them, we can assess if the consistency is an indication of the reliability of the model. Of course, if we have a latent space, we can introduce and integrate all of them. It will be richer, but it will be a more complex approach that could be skipped by just summarizing and making more the feature within each of the methodologies. So by analyzing separately each of the techniques and each of the methods that we presented before, and giving just an indication of a discrete value, a binary number of how is the state of the person in this particular moment, we can skip all this problematic of integrating in a real term or in a real way the signals between them. But of course, yeah, in a follow-up step, we can try to see if a latent space could include all of them and try to see a underlying or mechanistic dynamics that is creating the whole dynamic of the system.
Yeah, okay. Yeah, makes sense to start simpler, I guess, because you can have all sorts of complicated interactions. You can have synergistic interactions. So maybe two measures independently, they don't provide anything meaningful apparently, but when they are combined, they give rise to something that is actually meaningful. So
yeah.
And could you maybe go into the whole feedback loop system again the last year?
Yeah.
Could you describe that again?
Yeah, maybe someone else that is working in the reinforcement learning module wants to jump in to have more detail, or
Well, yeah, I can explain. Yeah, okay. Yeah. Hi, I'm Angela. You are hearing me from the same mic because I am here next to Sebastian. Yeah, okay. So in this loop, well, first, a lot of things here are still questions, are one of the things that we wanted to clarify today. But essentially, what we are trying to do is, and in this case, you are seeing an example of an actor-critic algorithm. This diagram is based on PPO. But the idea is that we measure the state with a combination of the state of the participant or the user and both the dashboard. And we are now exploring, at the beginning, we wanted maybe to synthesize the dashboard maybe with CNN or some machine learning algorithm based on images, but now we think that maybe we won't have enough data. So we are thinking about some features of the dashboard, for example, some features explaining the complexity to give the agent some information on how the dashboard is, and also some information on how the user is. The reinforcement learning agent would choose an action. Now these actions are linked to changing, for example, the shape, the color, or all of these combinations as Sebastian was explaining. Now it will be actions. So you will end up with a new dashboard that will be another state, and now the reward is a combination of the mental workload variation based on the different cognitive signals that Sebastian was explaining. For example, he have shown that we have seen difference in the pattern of fixations, or difference in the features obtained through EEG, or difference in the response time. So the idea is to measure before and after this action or this change in the dashboard, and study measure the reward. This is why it's multi-objective, because we are changing both the dashboard and we are obtaining different rewards depending on the cognitive signals. But still, we are thinking if it's better to have a different reward for each cognitive process, if it's better to measure all of them, if we need a baseline, and we are measuring in comparison with a baseline, absolute values, and so on.
Okay, I see. Thanks for that.
So I don't know, Ioannis, if you want me to continue to the next challenges to bring it to the table, or what is your proposal?
The next challenge meaning the multi-objective, or
No, so I can continue as we framed as to present what we illustrate as challenges, and then we can, if you want, come back to the ones that.
That's fine.
So the first one that I mentioned before was the data scalability, so amount of data available at disposal to discuss. The second challenge that we want to provide and to bring here to the table to discuss is the how to operationalize the data. As Miguel was commenting before really accurately, okay, how can you make the signals integrate within a reinforcement learning driven module? And our idea was to make a summary of each of the measurements into discrete or binary values, as you can see here in the figure. So if you have the neurophysiological descriptors, you can make a cognitive load assessment in which each of the features indicate the state of the individual in that moment, which could be a discrete weighted value, an array, or just a singular value of high or low cognitive state, and use that to reward to train the reinforcement learning module. So yeah, we are still, as Angela was explaining, debating and analyzing how to approach this problem and how to tackle this challenge.
Yeah. Cool, thanks. Yeah, I don't know, Carl, do you wanna do as always and have your like general feedback at the end, or because I feel that this meeting is a bit different, so maybe
so I can continue and then wrap up and then come back as you prefer.
Yeah, how do you feel, Carl? Do you wanna like wait until the end as always? And
Yes, I think so. You can see all the challenges in context of each other. Yes.
Okay,
Okay,
so let
cool.
me just present all of them, and then we can come back to the points that you feel more pertinent to discuss. Okay, perfect. So I mentioned about the data scalability, how to operationalize in the reinforcement learning. Another challenge that we are assessing now is how to measure this expertise that I mentioned before. So we want to see how to create these pseudo experts. We have different levels of expertise of the participants. One of the proposals is to reuse participants that we already assess from individual adaptation, individual visualizations, or maybe training them, new users, for many hours or many days before testing the combined environment. We are now discussing which is the most optimal way, or maybe we are not missing here or something that we should keep in consideration when trying to assess novice against expertise in the participants. A further challenge is about exactly how to do a model of the cognitive state, how to integrate all this information, this multimodal integration to assess the cognitive state. So as you mentioned before, Miguel, so there are many ways we can predict mental workload. What we are using now are just simple machine learning methodologies, mostly classifiers, to try to separate, to disentangle how is the state, the profile of the participants. But we know that there are many models that we can apply to get rich information of this data that is really complex, and maybe we can be profiting more by integrating really complex data together. And lastly, as individual point, we are also with the challenge of the population variability. As we are all familiar, we have some sample bias because of the location we are living. We are collecting data from Barcelona and Luxembourg. So of course, we have some lack of diversity in the population that we try to compensate, but we are trying to see how we can contemplate the population diversity that is not captured in our data, so we can transpolate the result to a bigger population audience by including or maybe profiting from some open source data sets or any other proposal that you can provide to us. And just to wrap up, we want to know your opinion about the task validity, what we have done, and if you have any proposed alternative, suggestion, or comment about anything we have presented today. And with that, we can wrap up. And thank you for the attention and the time that you provide us today. And we can discuss as much as you want in detail any of the points we discussed today.
Thank you so much, Sebastian, and well, the whole group.
Thank you.
Thank you so much for the presentation. I was just curious, how many, like, more or less, like, data points, if you want to call it, like, what's the size of the data we're talking about here?
So for this experiment, we had 120 trials, so it's around half an hour of data. So 120 trials of a few seconds each of the methodologies. So you have all of the data for EEG, eye tracking, heart rate, EDA, and behavioral.
Yeah, okay. Yeah, so you need like a really very sample efficient model to optimize. Yeah.
Of course, that as we have many visualizations, this amount increase as we include more trials, but then we have statistical combination that we have to keep in consideration that it's not the same profile or the same information coming, of course.
Yeah, exactly. Okay. Cool. Yeah, if you want to add anything else, or if you I don't know if you have like any specific questions or comments to Carl, like maybe any specific feedback you are looking for.
Yeah, maybe Ioannis or Luis, if you want to jump in for this, yeah.
I mean, we would like to hear some general impressions about this setup and the challenges that we have. See, if you have some insights, some ideas how to move forward, basically. So it's basically an open-ended question, right? It's like to have some kind of brainstorming, like Sebastian indicated at the beginning of the presentation, just to hear your general opinion, your sentiment, about this setup.
Cool. Thanks. So I see Carl's already there. So whenever you want, Carl can jump in.
Right. Well, I want now. In the sense that was an excellent presentation at many levels, but specifically because I think it did clarify exactly the kind of feedback that you're looking for, and presented very clearly the challenges ahead, along a number of key aspects or directions of travel. Before I start giving feedback, bear in mind you've been thinking about these things collectively for years, possibly. So don't expect any magical answers from us who have just now started to get a sense of where you want to go from this. But certainly this would be a useful opportunity just to brainstorm and discuss potential solutions to the particular challenges that you have brought to the table. Before I do that, though, just to make sure I've understood the end point of symbiotic, how could you just give me a very, very simple use case of if all of this is successful and validated and implemented exactly as you anticipated at its inception, what kind of technology or functionality or app would you be able to give people? Could you sell, for example? So pretend you're a startup. What is the problem you're trying to solve? And can you give me a very simple example, perhaps taking where you started, which I thought was a very good example. I am a theatre nurse in a hospital, and I have a VDU reporting various biometrics from a patient who is undergoing anesthesia. Now, what is your technology going to do for me as that theatre nurse?
I can address this question if everybody's okay. So Carl, the example Sebastian presented in the first slides, it's not actually one that we proposed as a use case. Perhaps I can refer to the use case we're examining. Some of the potential applications that we are considering is in the context of criminal forensics platform that has been developed by one of our partners. And these visualizations that we showed earlier, the graph-based or the distribution-based or the timelines, they are all based and inspired by actual visualizations that they are used in their platform for law enforcement agencies. And these visualizations show different aspects, different views of the same data. So you, for example, you have a criminal network which you can visualize as a graph, but at the same time, if these people perform phone calls and there are like CDRs stored somewhere called records, then a timeline perspective of that is much more useful in order to understand who is communicating, contacting who, for how long, and to what end. So one of these applications that we foresee is in such context where people may have to decide very quickly in the moment, or as the other use case suggests, the novice to expert transition, we want someone who is a junior member of a law enforcement agency to be able to understand, kind of like an expert, the context of a crime case that they're investigating. Another application would be air traffic controlling, where you have these very complex visualizations, a lot of information to digest. It could be even a dashboard that is collecting information during, let's say, a pandemic. These information visualization systems, I think there's a lot of there was a lot of progress done during, I believe, the pandemic during COVID, because people were collecting information and accumulating it and aggregating it to be able to give an overview of the situation. And I think all of us were exposed to that, and all of us found it very useful when we could track online the situation in a city, in a country, of what is happening, to make sense of what is happening. And obviously, okay, the clinical practitioner who needs to make a decision based on some data, that's another use case. So we have this either time-sensitive context where people have to decide fast within a few seconds, make a critical decision, or situation-sensitive or context-sensitive, where there are a lot of things to digest, to take into account. These are the two, I would say, challenges we're addressing, and as well as the And in parallel, we're trying also to see how also we can make that possible for somebody who's a novice and they have to transition, become an expert, but ease them into all this complexity. Obviously, I think for me the best example is when you learn to drive. Your parents take you to a kart, and all you get is a four-wheel vehicle, small vehicle with a wheel, not a gearbox, nothing, not a radio. You don't have these gauges that an accelerometer and all that, speedometer, and you just learn the basics. And as you advance, you get a proper car where you have all these, accelerometer, speedometer, and all that. You have the gears and everything. You are able to handle more complexity, but at the same time, it's kind of optimized. And then as you progress to become an expert, you can even be an F1 driver where you have these very, very complex dashboards, which look like a airplane cockpits, basically. So that would be an analogy I would draw. I don't know if that answers your questions. If not, please.
Yeah, no, it does very nicely. Thank you. Yeah, no, I see. So, I mean, there are, if I were to summarize that, there are two aspects to the ambitions, though, the use cases that you are aspiring to. One is the most efficient way of getting information from visual displays, and that would be best exemplified by the forensic example. And two, learning how to become more efficient and having the right scheduling of the format or the way in which data are presented to optimize the transition from being a novice to being an expert data forager or epistemic forager. Would that be just to sort of delineate the two in terms of, so what I'm thinking here is you have an impressive array of biomarkers, ways of phenotyping people's data foraging, visual data foraging, that could now be used, if validated, to assess not just the way, the format in which the same information is presented, but also the curriculum of presenting data in different formats that enables very fast learning to become an expert interpreter or forager of those data. Would that be fair? Just to sort of tease apart some of the agendas.
Is that a question to us?
Yes. Well, I'm just asking for confirmation.
Yeah.
But does that make sense? Because if just in a very simple minded way, I could read the one of the ambitions of the program as to find for the average person the most efficient way of presenting the right kind of data. So take the epidemiological example. I just want to find the simplest, most informative way of presenting my pie charts or graphs or tables, such that anybody on average watching this would get as much information, in fact, as easy as possible to assimilate the information that I am trying to convey. That's a very different problem from training somebody, say, training somebody to be an airline pilot with flight simulators. Using your driving example, there will now be, it's not a question of presenting the right information in the right way, but presenting the right information in a format that enables people to learn how to sample that information and to actively look for different formats or choose different formats or to go deeper into information. So that sort of the example with the driving the car, that seemed to suggest it's not just a question of taking the same information and presenting it in different formats. That you seem to imply that as you become more expert, there's more fine-grained information available that you don't need. So it's not just the format of the data, but also the data content, the informational content, which could be increased as you become more expert. So I'm just clarifying that that is part of the part of the agenda.
Yeah, that's definitely part of the agenda, and you put it very accurately. I'd like to add that on top of what you just commented on and described, it's also important for us. Another exercise we're trying to do is shift the focus from the cognitive processing to the and leverage, let's say, the visual processing capabilities we have. So not only transition to something that people can understand more effectively and efficiently, but understand when to do that. So it's important to keep in mind that if somebody is like mentally overloaded, we don't want to necessarily take that person away from the control room, because they might have to stay there. But instead, we want to adapt the environment to support that person's capacity to apply proper decision making, accurate decision making, by taking them temporarily off the F1 car and putting them on a small cart, and then switch them back to the F1 car when they're ready to, as you said, forage all that information and digest it and process it.
Yes, excellent. Yeah, and that's what I meant to imply by the scheduling the right training session for this kind of and that agenda, I think, nicely speaks to the fact if you've got good biomarkers of physiological or eye movement biomarkers of the efficiency with which they are currently coping with this kind of information, then you can also use that to indicate, well, it's time to move on to the next kind and the next, more and more detailed information. But as you're intimating, it all rests upon establishing the validity of these biomarkers or biometrics that reflect the efficiency of the information processing, and more importantly, the foraging or the active part of gathering the right information in the right format, or choosing the way in which you assimilate that information. And specifically because you're dealing with visual displays, I get the impression that we are talking very particularly about active sensing and active vision, which actually reduces to something which may sound a bit too simplistic, but I think is an important simplification. We're just talking about where to look next. So we're now talking about the cognitive processes that underwrite where should I look next, and how long should I look there, and where is the next most important piece of information coming from. I say that because in terms of the paradigms in interpreting the physiology and interpreting the galvanic skin responses or the heartbeats, that putting active vision into the mix as the actual task, I think is a useful thing, because you can now refer to literature that is involved with visual attention, active visual searches, not just in neurobiology, but also in the clinic, in people studying, say, neglect syndrome. So there are certain tasks that bear a similarity with what you are doing that you could refer to, not necessarily use, but just say, this is exactly the kind of task that has emerged as the most diagnostic kind of task in neurology when studying people with hemi-neglect syndromes, for example. And this is, we're using this as a motivation for pursuing this kind of task, using the same kinds of metrics that people in the neurology clinic would use to assess the capability of this person in terms of their ability to search for information visually. So I'm trying to motivate a particular view of the problem that you are, a particular view of what would be a good format, and implicitly what would be a good scheduling to train people to use their visual foraging in the most efficient way, and to have to use your paradigms as ways of validating the non-behavioral measures. So I'll give you my feedback in terms of the first challenge before, just to contextualize the feedback. I have to say the reinforcement learning approach, for the very reason you're stating, I don't think is a viable approach. And I say that because if you're using a reinforcement learning approach, you're basically trying to identify a state action policy or a mapping from one thing to another thing, which can be learned. But of course, if you're now dealing with intersubject variability, and if you're dealing with people who are on a journey from being a novice to an expert, then you're introducing a certain context sensitivity that will make the reinforcement learning paradigm extremely difficult to do, even beyond not having enough data. You could certainly build a model of this person's brain doing this task and then generate surrogate data, and we can certainly talk about how you might do that, and then you could train your convolutional neural network or your variational autoencoder or your transformer model to say, well, it's more likely they're going to look in at the quadrant of the screen that has this kind of format, so we're going to foreground that visually. But that would only work for that patient at that point in their journey from being a novice to an expert. So you'd have to redo that every time for every person that you might want to do, and of course that's not going to be practical. On the other hand, if you can use all of the proxies or direct behavioral measurements of the efficiency of the active visual searches to test various protocols in terms of format or in terms of training schedules, you can take this person at this stage in their expertise development, present them with a battery of different formats, measure their responses, both behaviorally and physiologically, to this battery, and say, for this person, it is this format that is the most efficient at this point in time. And then you could repeat that during the learning process, to then not use the physiological and behavioral markers as the object of training in a biofeedback, but in a more simple-minded way, simply using these markers to determine what is the best for this particular subject in this particular context. So now you now take charge of which things you are going to present the formats, for example, and then assess the response of the subject to the different formats, and then select the format that is best for that subject, and then repeat that kind of procedure for a subject that's trying to learn from being a novice to becoming an expert. That seems to me a much simpler approach that eludes the problem of trying to in a personalized medicine-like setting actually learn what's going to be best for this subject. One of the reasons I'm saying that is that if you wanted to use actor-critic models or reinforcement learning, you're probably going to be using some kind of backpropagation, which means everything has to be differentiable. Yet the things that you are changing are discrete. They are not differentiable, not continuous. You're not slowly morphing from semantic textual information to color or shape information. It's either like this or it's like that. So there's a discrete choice, which means it's going to be very difficult to use standard deep RL approaches to incorporate into that feedback. It strikes me that there's a very limited number of ways of optimizing this the format of these data for example, and a sufficiently small number that you can just present all the different options and then measure the responses to the different options using your validated measures, and then use that to say, well, for this subject at this stage in their learning, this is the best way forward. Can I get your response to that? Because I may have missed something in terms of what you wanted to use the reinforcement learning for. Who's a champion of reinforcement learning here?
Let's go with Saravan, and then we can all comment.
Yeah, it's not about that order. I have some more pre-defined questions before getting into that problem. So here, mostly we try to solve about user state with respect to the information need to be presented. So the system should know what is the user seeking, also user current capability. So based on that, the system is keep on giving the information such that the person after a certain point, he will able to attain this desire from the information. So now I can see this problem as a functional approximation where we have X is a user, Y is a state of action space. That system is going to give us a suggestions. Now my point is, so far from the neurophysiological perspective, so we couldn't even find many input states. We have only one kind of input, that's also kind of discrete one. So is there any way to get a continuum input space from the user perspective? Example, Saravana as a user, I haven't experienced towards the information visualization system. Whereas once if I start looking at the information, the system should know, okay, how the Saravana is pursuing the information, whether he's getting his desired content or not. So the system should understand my state and will be keep on giving the information such that after a certain point, okay, I can get the information which I needed. So this is the general problem. Whereas here from the user perspective, is there any neurophysiological markers where can I get for this continuum input space?
Yes, I see. But to explore that input space, you're going to have to, what are you going to do? Are you going to use an e-greedy search, or how are you going to evoke changes in the physiological markers of the efficiency, or say the arousal that I'm not, I am currently not able to converge or infer the information that I'd like to sufficiently quickly. I'm just thinking about the practicalities. I was just trying to imagine how on earth one could do this practically in this particular setup. If this was just if this was, for example, pointing a camera, say you were doing surveillance with a camera, say at an airport, then I can certainly see, because you've now got continuous control variables, that you could sort of start looking over here or looking over there in a way that would give you the most informative information given what the computer or the person knows at the moment. And you could certainly now use continuous feedback and to use reinforcement learning. The problem that I can see is, it's not about presenting more information. It's about presenting information in this format or this format or this format. So you can't continuously move from this format to this format, or can you? How did you imagine
that's what we have one findings example. So when we show the graph with all the text annotations, if it's simple questions, the brain responses were more spontaneous. When we have a lot of visualization and adaptations, because people already knows about information about the color, shapes, and everything, so we have got more linear activations if you give more information in terms of visual primitives. So from this perspective, I can make, okay, when there are no information about the system, when the subject is initially pursuing the things, there are more spontaneous activity. Once if they keep on learning about, okay, color belongs to gender representation, even if they get some more information from the system, then the activities are more coherent and it's more towards linearity. So if I'll make my X input space, amount of linearity from less linear to highly linear. So now, is there any other biological marker from neuroscientific perspective to decode this input space? Because we have a lot of action space from the output. So now we are trying to struggle to get what is our input space, how we can extract this neurophysiological information from the input space. So that's our major goal over here. Is Ioannis.
Yeah, no, sorry, I didn't want to interrupt you. Whenever you're done, I just
Okay,
go on.
so this is what we are trying to struggle, because we can get cognitive load, whether it's higher load from the eye gaze information. Through the EEG also, still we are exploring. So we have found only this linearity level increases, more synchronized activity across the brain region. Okay, if you increase the more visual primitives into the system. So now what we want to find out, so if you know, like, okay, so you have access and input space, you have a, it's a continuous space, then we can easily do the functional mapping from input to output Y. So now we are struggling, what is our input space X? What are the marker can I extract to get the user a present desire? Example, so where there is no feedback, suppose I'm looking for, from the crime investigation database, I'm gonna look how many persons are in prison. The system doesn't know whether Saravana is looking the prison status or not. So first it will show some information. I'll be keep looking. Suppose I want to know the intention. System should know what Saravana's intention, whether he is getting he's happy with the information with the system is presented. If not, the system is keep on presenting the information. Once if I get the information about the present status, then through the physiological parameter, there should be a changes in the parameter. So the system understands, okay, Saravana is interested towards this. Let's give some more information about that. So the system should change in that way such that that information visualization will work based on the user needs. So here we don't know, system doesn't know what the user is need. So that's what is a research gap, what problem gap, what are we looking or seeking? From the neurophysiological perspective, can we track these kind of information from the humans through EEG or through eye gaze information or etc.? Is there any other markers from your perspective?
Yes.
Sorry,
Well, we can certainly come to that. So let's to see if I understood that then. So this is not quite what I had understood in terms of the use cases, but what you're saying is that there is going to be a sequence of new information that has to be assimilated, and that you can use the physiological or behavioral markers to infer when the subject has concluded and assimilated this information. Now it's time to move on to the next one. And furthermore, you can actually guess what kind of information that people in general are going to want to see next, so that you are scheduling the presentation of sequential information in a way that is informed by the inferred cognitive state, where you're using the physiological markers to infer the cognitive state. Is that what you were intimating? So I'm trying to imagine what kind of setup, so I get a sort of a table of options, and it takes me a bit of time to scan through, and then I'm more likely to choose one versus the other, and the reinforcement learning will now recognize, oh, I've now assimilated what options are available. It's now time to choose, and it will have some prize about what I'm going to choose, because I choose that kind of information, and then successively. Is that the kind of functionality?
May I recap maybe, and please, Angelo, Saravana, Luis, feel free to correct me if I say something that's not accurate. The basic, if we cast it into an RL problem, the basic setup we are looking for is, first of all, we're looking into an environment that consists of the user and the dashboard. So we collect information obviously about the user. All this cross-modal information that we use to create an embedding, what we call a compact representation of the user state. So we try to reduce the complexity of the neurophysiological signals that we collect into a small vector that we can use as input for our agent, and aggregate on top of that, complement that with information about what the user is looking at. So some information about the dashboard itself. That information could be configuration settings, could be how many elements are present in the screen at the current moment, and so forth. But useful information that we feel captures the complexity of the visualization. Now, as we track in the moment the user's mental workload, and there are much better than me, there are like indices that capture that. And again, you put it very quite correctly when you said, this is something you have to tailor for the user. So we have we assume that in our case we establish a baseline. We know what the baseline is for that particular operator or user, and we know when the signals will get deviate significantly from that baseline, and we can assume that the user is overwhelmed and overloaded. And in these moments, in these time steps, the agent has to pick from a limited action set what adaptation to apply. And obviously that's a discrete set, as you correctly put it. I mean, we are not looking into a continuous set. A continuous set would be much harder to train in an offline setting. We discretize it to make it simpler and easier. And this action set is basically a set of simple individual adaptations, as we call them. We change one thing at a time, not all together. But if you, in principle, apply all individual adaptations, you'll get this, let's say, full adaptation, fully adapted version of the dashboard, which we have tested experimentally and validated that it works. We have also tested the individual ones, but let's say the bulk of data we collected are about all the adaptations put together, and we have a limited subset for the individual adaptations. So what we want to train is the R agent to know, given a particular state of the environment, like the state of the user and the dashboard, which individual adaptation to apply next, to optimize a reward function. That reward function could be, I want to reduce the mental workload, optimize decision-making time. It could be a multi-objective function with 2, 3, let's say, variables that we consider important. I agree with you. The architecture has to be very simple to reduce the amount of data we need to train the agent. That's definitely something we are considering and we've implemented. But because of the other problem is because the proposal has been accepted and we are implementing it, I'm not sure how much we can deviate from the original proposal of considering casting this as a control task and considering something that's RL based and make a 180 degrees turn and consider something different, very different. I don't know if this helps clarify or disambiguate the questions, or is there something else?
No, absolutely. Yeah, it was very useful because it was exactly what is being adapted, and now I have in my mind a multi-panel visual display where from time to time one of the panels will change in its format, and that change will be optimized in relation to the inferred cognitive load that the subject is currently experiencing. So it's a scheduling of the different formats, which could also include presenting the next page of information and the like. So yes, you've been very clear. You have to use reinforcement learning because that's what you're paid to do. So one way to motivate that is to use the notion of amortization. That if there is some optimal selection of the right format and that can be learned by a reinforcement learning scheme, you can basically look at that as amortizing the right kind of foraging. What does occur to me, of course, is that the subject herself will know exactly what the right kind of foraging is by choosing which panel to look at. So, for example, had you got the same information in different formats. You could simply use eye tracking to infer what is the most efficient way of assimilating this kind of information, and you could then use that. You could then learn how this person optimizes her visual foraging. So you could certainly, I imagine you could certainly amortize that kind of mapping. Again, coming back to the notion of the reinforcement learning being a sort of universal function approximator. What is it approximating? Well, it's basically approximating the visual foraging of this subject. What does that mean? Well, it's basically optimizing the mapping between the behavioral physiological state, including the visual input, what's on the current screen, to the next action. And then what is the next action? It is, where am I looking next?
One clarification, not so much where the user is looking at next, but rather how should I adapt what the user is currently looking at if I detect that the user experiences a difficulty into processing the information or understanding it, and the user feels overwhelmed and overloaded. So it's not so the users can freely look whatever they like on the dashboard, but when they focus on something, our job is to determine if we should simplify it in the moment. If we should serve it a bit differently by doing these small tweaks in the adaptation, these individual small changes, incremental changes. Is that clarifying?
Yes,
maybe the...
It is. I'm just trying to imagine how one might do that. You say you've done it, and you have a proof of principle. So so how would one implement the incremental changes? Would it be replacing a bar chart with a pie chart, or would it be?
Yeah, I can give you an example. Actually, if we have some maybe we are preparing the next series of experiments. If everybody's okay, I can just share some examples. Allow me to give me one second. This is going to take a second. I'm just opening a lot of windows now. Okay. I think I'll just share my screen. This will make it easier. Okay, so again, sorry, I was not prepared to present this stimuli, but I think this is just one example. This is a graph, a distribution, as we call it, where people see the number of calls that have taken place in a timeline during, let's say, 24 hours. This is what, let's say, we would call the basic version, although it's not entirely correct. The color should be uniform, not gradient. But imagine it's a solid color, not you don't see this gradient. One individual adaptation would be to instead of showing this, let me find another example, is to introduce information about the day and time. So one of the things we are doing is we maybe not so clearly demonstrated here is we use the color coding to denote the end of the day. So here you see the change of the day switching from 1100 to 0000 hours, and we also using this gray block to indicate what's the daytime and nighttime. So within, let's say we have this convention between 5 or 5:30 to 8. It's daytime, we assume it's daytime, the rest is night. So then our questions that are about identifying the maximum number of calls taking place during nighttime we encode that information about nighttime. We visually encode it compared to the baseline, which doesn't provide that. Another information is the gradient, which we use to highlight or make more salient the larger values, the values in the greater numerical ranges compared to the smallest values. And I'm not sure if I have another individual adaptation is the use of bars as geometric objects instead of using the distribution, which is continuous here. So making these more discrete, more easy to identify. So we are playing with a lot of these. And here you see an example. If we transition from a baseline version to a fully adapted version, now we have information about when the current day ends and when the new one begins. We have information about nighttime, daytime. We have using color coding effectively and the gradient to indicate, to make more pronounced the larger values. So we don't rely just on the shape, but also on the color. We also provide additional information, again, color coded using shapes to indicate the largest percentage rate of change, positive or negative. And again, all of these, the plan is to test them via a set of questions that we ask, which consider either one variable or more than one. So for example, a univariate, let's say, a question that examines only one variable would be, okay, what's the time where we observe the highest number of calls, which would be like 8 o'clock in the morning. But if I change the question to consider two dimensions, two variables, like what is the hour of the within the 24-hour window where we observe the largest number of calls during the night, now I'm adding the other dimension, and so forth. So we have questions of varying degree of complexity, but also we can adapt the complexity of the graph itself to show more information or less information. Does that? I hope that provides some context. I don't know.
Yes, no, absolutely. I mean, I think the basic idea and setup is beautiful. I'm just trying to see how you'd use reinforcement learning to optimize that. One way of thinking about this is that you've got a number of additional features, such as the graded coloring. You've got sort of addition of daytime and nighttime. So how one can imagine moving from different formats in a graph, as it were. So are you thinking then that I can progressively, given the question at hand, given the task setting, move through increasingly more informative procedures, and then when the subject is overwhelmed, move back on the graph, so that you're converting the display format into effectively a Markov decision process, so that you're moving around on the nodes of a graph, each identified with a particular format, and then moving around so it's more or less complex in a way that you can learn that this is most conducive for this particular subject to assimilate on the basis of both the explicit, the accuracy of their answers to the questions, but also the number of eye movements, their heart rate, and the spectral ratios of, say, theta to alpha as proxies for the efficiency. Okay. So yes, I mean, I'm distracting you. So this is for my personal interest. Perhaps we should move on to ways of validating the particular meachrements or motivating the particular data that you are acquiring in relation to computational neuroscience models of this kind of information gathering, this kind of actively sampling the data and then assimilating it, and then looking somewhere else in the visual scene in order to assimilate that. This, I think, is addressing challenge number 2. I think it was number 2, where, or possibly 3. Good, right, yeah. Actually, yeah, let's go to the data how to operationalize the signals. I think the answer to that would rest upon establishing the predictive validity of the various signals in relation to the inference implicit in the subject being able to assimilate the information. So in my world, that would be effectively looking at the behavioral and the neuronal correlates of evidence accumulation. And that is in principle can be addressed by modeling, having a sort of digital twin of the subject that is exposed to the same kind of information, and modeling the evidence accumulation, and doing it in a way that is biologically plausible, so that you can now generate the same kinds of responses that you can measure, basically the signals. I'm assuming here the signals in question are a whole range of signals that range from the accuracy of the response to questions through to the number of saccades, the dwell time on the saccades, through to galvanic skin responses, possibly pupillary dilatation, right through to the EEG, the spectral profile of the EEG. Is that what is meant by signals here? Yeah, brilliant. So I don't know that you're going to have the time to do this, but you could in principle build a model of the subject who's actually trying to assimilate the data, and make it practically very realistic, so that they actually have to foveate different parts of the screen, and assimilate different complexity of information, and that sort of could be easily modeled by the number of points at which they had to saccade to assimilate the data. So that was nicely exemplified by having the gender of the subjects in written as letters, where we'd have to actually foveate the particular letters, as opposed to just looking in that triangular region of the visual field just to see the background color, for example. So that would, if you actually started to model that, would be a difference between having to focus on a very specific part of the visual format versus not having to make so many eye movements. And you should be able to, one could in principle actually simulate that, and then show that in the simulations this corresponds to a smaller number of eye movements, a longer, a reduced reaction time for convergence to a particular inference. One can also simulate the electrophysiological responses and show differences in different spectral aspects, all in the service of, first of all, validating the signals as appropriate measures of what you want, which is basically a fast and efficient, fast and frugal in a gigarenza sense, data assimilation or evidence accumulation, but in the context of active sensing. But also that would afford the opportunity to generate the surrogate data that I think is possibly challenge 3. I can't remember now. How to create, by pseudo experts. I know that's a different one, right? It was a cognitive state model. So if you wanted a cognitive state model read as a generative model of the kind of data assimilation or information assimilation behavior that you are inducing in each of the subjects, then in principle you could build models to do this and use those models to generate surrogate data that then could be used for the reinforcement learning. So the model here may be distinct from the model you had in mind, in the sense it's you would actually have a generative model of different cognitive states that would then effectively drive the exploration of the visual information in the most efficient way possible, and in so doing generate both the behavioral and the physiological responses that you can actually measure, thereby generating surrogate data. The way that this graphic suggests that you may be thinking about it is that you have some assumption about the cognitive state. So in my world, you would build a model that had cognitive states. It would have, it would be, for example, a Markov decision process, a partially observed Markov decision process model that was itself examining the visual display by looking at different parts and trying to resolve uncertainty about the information about which it was going to be asked. And then that process would be a surrogate, a digital twin of the actual subject that you could then use to produce synthetic data, I repeat, both behaviorally and in terms of eye movements, possibly even heart rate, and in addition, the spectral or the electrophysiological correlates. So there are examples in the literature of all of those things, and I can briefly take you through examples where this has been done. I don't think it's going to be appropriate for you to actually emulate or to do this, but what you can do is use it as an example of why you have chosen these measures and these particular operationalized signals, why you're taking these particular signals, because then you can refer to when one actually simulates this, then these particular responses do actually report the changes in the cognitive state. So it's a slight reversal of the direction of travel implicit in this graphic here. All you need to do is to show that your measures, the 5 measures you have here, are veridical reflections of the degree of being overwhelmed. So, you could describe that in terms of uncertainty about what to do next, or uncertainty about the information that is being conveyed on the screen. And once you've done that, then any of these, or a mixture of all of these, would be appropriate measures then to put into the reinforcement or the amortization screen. The amortization scheme. Does that make sense? It might make more sense if I gave you a few concrete examples of the kind of studies in computational neuroscience and clinical neuroscience that provide worked examples of this kind of approach.
Definitely, some examples would be appreciated. And so, but I have maybe some small questions just to understand better the suggested approach. Is a digital twin would that also require the collection of substantially large data set and the acquisition of signals and also to put to make the acquisition within context, like not ask people to look at stare at the screen for 3 hours and show them different visualization, but ask them to perform, I don't know, a series of tasks. Which, if that's the case, this is extremely difficult for us because the experimental design is kind of detached from the actual platform. We are now kind of recreating, in a way, simulating the platform environment. But as Sebastian presented, we're doing this in this single trial experimental design where we show a stimuli, we ask a question, we show the stimuli, we get a response. If we expose the user to the real environment, at least to my understanding, I don't know how we can control confounds and interactions and how this would work. But if you have suggestions on papers that have tackled something similar, that would be very appreciated.
Right. Yes, and I'll go through a few that may or may not be relevant. As I say, I can't promise this is going to be useful because you've been thinking about this for a long time and I haven't. But in answer to that question, yes, I'm not proposing that you create a digital twin of each subject. I meant merely create a universal synthetic subject for the paradigm, the experimental paradigm you're using. And then you have an ideal Bayesian observer that is faced with the same challenge that every experimental subject would be faced with, namely, how do I quickly forage through all this information? And again, this has to be very realistic, and I do keep on emphasizing eye movements here because there is only one way that I can act in this situation. When I'm looking at a screen, the only way I can change the world is by moving my eyes. There's nothing else I can do. So in this context, well, that's not quite true. Of course, I could press a button and change the format to be bar charts or pie charts or ask for the next layer of information, and that could also be modeled. But let's just keep it simple and keep it that I've just got, for example, a visual display with the same information in 4 quadrants, but supplied in different formats. And my job is now to look and foveate in the most efficient way the information to resolve uncertainty about a key attribute of the information that that corresponds to what the question is, the question that the subject is trying to answer. We don't need to model the answering of the question. All we need to know is I have to resolve my uncertainty about the number of phone calls made in the nighttime, for example. And then you just build an ideal Bayesian observer of this scene, but equipping it with the limitations that the real subject will have, which is they have to do the foraging around and they have to decide where to look next to get the maximum amount of information in the quickest, as quickly as possible, so that when they are compelled to, or under ideal Bayesian observer assumptions, they will go and look at the most information-rich part of the screen. So you sometimes cast in terms of salience. So we're now talking about the visual search literature, that I want to look, sample the visual information in a way that maximizes the expected information gain. So this sometimes cast in terms of salience maps that I actually have in my head. I'm inferring now a salience map, which means I should be looking over here as opposed to looking over there. And I look over here, I resolve uncertainty, and then given my new beliefs about the scene, I now have, and the next place to look would be over here. So you can simulate these things, and in simulating them, you can now generate from this synthetic subject the kinds of things you can measure. So, for example, reaction times. You can measure where would the eye tracking tell you that they actually looked. You can even simulate the electrophysiological correlates of technically what would be the belief updating whilst they're doing this kind of thing. So you do this just for an ideal subject, and then ask, if I now change the stimuli and make it more complex, will my synthetic subject show the expected changes in the spectral profile or the prolongation of response times, or will they perform more saccadic eye movements before resolving their uncertainty, and thereby validate all of the measures that you've used? You can then, in principle, do something called computational phenotyping, which is optimizing the model of the subject, this ideal Bayesian observer, who is basically generating their responses on the basis of a generative model of what is causing their visual input, that entails priors. So by adjusting the priors, you can actually get the model to reproduce a given subject's behavior, and then that would be more like a digital twin. You don't have to do that, but you can do that. Furthermore, you can do it in a way where it's not just the reaction times or the decisions that they make, but also optimize it in relation to the neurophysiology or the heart rate. Should you want to? This would be an enormous undertaking, but I repeat, you can say this could be done, and if we did it. And when people have done this kind of thing, these are exactly the behavioral measures that emerge as useful measures, and therefore validate the particular data features that you've chosen. So what I was doing was trying to go through the literature, highlighting examples outside of your field where these particular data features, were important measures of the belief updating and the evidence accumulation, using a model, an ideal Bayesian observer, effectively faced with this problem of abstracting information from a visual scene by moving your eyes around and choosing what to look at next, making decisions about how to reveal the information or solicit the information that affords the greatest reduction of uncertainty, or technically maximizes expected information gain. Does that clarify things or make things easier in any way? Well, perhaps I'll share my screen and just take you through what came to mind during your presentation as potentially useful papers. That, I repeat, I'm not suggesting you do this. You'd have to get another Pathfinder project to do this, but you can point to the literature and say it is doable. And when people have done this, they come up with exactly the same data features that we are actually going to use in order to predict the next optimal change in the visual display for this kind of what we refer to as epistemic foraging. So this is like foraging in an ethological sense, but you're foraging for information as opposed to rewards. So foraging for information means you're trying to maximize your expected information gain, which means you're trying to minimize your uncertainty about what is causing this visual display. And if it's very difficult to forage, you get overwhelmed and you're not able to resolve any uncertainty about what it is that you need to understand or infer in terms of what that information is meant to convey. So this fits very neatly into an active sensing paradigm, where you're treating the process of looking around the screen as an evidence accumulation under uncertainty. And the idea is you're actively sampling or asking for the next kind of information in a way that maximizes the rate at which you reduce uncertainty, and thereby efficiently reach an inference or a conclusion based upon the data that you're actively foraging. I think that would be the way that somebody in visual search literature as a neurobiologist, or perhaps even sort of machine learning and visual surveillance, neurorobotics, and would look at it. How do you actively gather the data? When you're in charge of the where to sample the data and possibly the format of the data. Do I enter a dark room? What's my first epistemic move? Well, it's to turn the lights on. Why? Because that reduces uncertainty about what I'm looking at. So that that's one important aspect of this sort of epistemic foraging. It's resolving the ambiguity about the data, getting the contrast right, for example. So you could have a knob on the in your experimental paradigm that gets where the subject can actually choose the right contrast in order to maximize their expected information gain. But that would require them to decide. To what degree do they put the contrast in the sort of graded shading, for example? You know, what's the most useful for them in terms of resolving perceptual ambiguity or maximizing expected information gain, given what they believe at the moment. So that's the basic idea. But let me try and put some flesh on that. I'm not sure I'm going to be very successful, but we'll have a go. So let me share my screen. And I'm hoping that you can see what's going on at the moment. Yeah, what I'm going to do is just very quickly scan through a number of papers. And I know this has been recorded, so if you find if there's a useful paper here that one or more of your team would like to go and prepare an executive summary of, that might be useful in motivating some of the data features that you want to feed into the RL scheme, then that's the purpose of this. The first notion, though, perhaps we shouldn't go for that one. Let's just. Oh no, let's just do it in the order. So, if you have in mind a particular ideal Bayesian observer model with this active sensing built into it, that you can actually simulate a synthetic subject doing the tasks that constitute your experimental paradigm. Because you're using a generative model, you can then adjust the priors on that model, of which there may be many, in order to make the ideal model behave in exactly the same way or match the performance of an individual subject. And that's called computational phenotyping. This is actually the wrong example, but has some key players here. I'm actually going to go and just find the original description, which is more of a tutorial. Computational phenotyping. Yes, a worked example. So this example was a kind of epistemic foraging task where we were simulating a little mouse that had to forage for information. So this mouse here wants to find its reward, which can be up here or up here, but it can only make 2 moves. And to make it interesting and to introduce this sort of active search and evidence accumulation aspect, it knows that if it goes down to the bottom arm, the color of this cue will tell it whether the reward is on this side or on that side. So it's a very, very simple paradigm, but it's has exactly this sort of epistemic affordance with this expected information. And if I go and look over here, I will learn something that has implications for my subsequent behavior. And you can simulate that. Right, how do I get back? Oh, yes. You can simulate that kind of decision-making under uncertainty kind of problem using a partially observed Markov decision process, and therefore start to generate both behavioral. So, for example, here, these are simulated behaviorals. These are sort of the beliefs of the little mouse. These are the decisions it made, estimated electrophysiological event-related potentials in this instance. You can also simulate things like dopamine, which is relevant for you, as we'll see in a moment. And then, having done that, you can then adjust the priors of this model in order to match the behavior of an empirical subject, an actual mouse, so that now you've got a digital twin of the mouse. So that whole procedure is basically called computational phenotyping, which is something that you won't do this, but you could certainly say that in principle this could be done once we've got the right paradigm and the right biological markers in play. And furthermore, if you can do that, you can now generate synthetic data. So there are people doing this, using this kind of scheme to generate synthetic data for autonomous driving, to actually generate human-like driving behaviors, to generate simulated data to train use deep RL to train autonomous vehicles. So this is what I thought you meant by pseudo subjects. I thought you meant synthetic subjects, but you didn't. But if you did have this kind of synthetic subject, this digital twin, you could now, in the future, generate synthetic data should you want to, or you could now start to say how this subject would learn if we intervened or changed the paradigm in this way or that way. So I thought that as a phrase might be a useful thing to have in the future as one possible next step. You know, after the initial you've met the initial challenges. This is a quite a detailed paper, but I just wanted to show it because it uses the same the paradigm that was simulated here, where in which we built a little brain that could do this kind of foraging, not in this instance for letters, but for sort of you know, an iconographic sentence, basically, where little pictures stand in for words and on different pages. And the problem that this agent had to solve was where to look next in order to resolve uncertainty about the sentence that the little agent was actually reading. So this is page 1, this is page 2, this is page, well, in fact, no, this is word 1, word 2, word 3, and to simulate the kind of eye movements that people make when reading, which has the same kind of flavor of the epistemic foraging that you're talking about, but you would be more interested in what kind of visual display would make this kind of epistemic foraging as efficient as possible. But you can simulate these things, and in so doing, perhaps not in this example, well, this particular paper explains how you can combine these Markov decision process models with continuous state space models that are apt for where the subject actually looked in terms of fixation points for the next good saccade, the saccade that maximizes the expected information gain, given what I believe about the scene at the moment. It also illustrates the use of deep temporal models. So as you're accumulating beliefs or information about what letter you're looking at, or in this instance, whether it's a bird or a cat, you're also at a deeper level accumulating information about the word, and also at a deeper level further over slower periods of time, the sentence, the information that you would need to actually answer the question, how many people made a phone call during the night time, for example. But here, this was limited to just a simple reading of iconographic text. So that's a technical paper, but just sketches the kind of architectures that you might use in building these synthetic subjects that do this kind of task, and in particular the mixed architectures that have discrete state spaces, apt for many of the for some of the examples you showed, whilst at the same time talking to a continuous state space model that would actually generate eye movements and reaction times in the normal way. But the reason I wanted to introduce this as a sort of technical description of the kind of models was to oops, no, not it did. Here. So using that kind of model, you can actually generate electrophysiological responses. And what caught my eye was your nice observation that things like P300s and N2s are important electrophysiological markers or correlates of novelty detection, recognizing that there is the opportunity, or the context has changed, but also there is an opportunity for information gain in the future. So when you simulate this kind of data or active sensing or active inference, because you're using biomimetic or neurobiologically plausible schemes, you can also generate synthetic event-related potentials. So in this instance, we were generating, deliberately introducing surprises in this little scheme here by actually changing, introducing the wrong word at the end of the sentence, and thereby eliciting or simulating these late, this will be a positive P3 or P300 here. So what I'm saying is that in computational formal models of this kind of active sensing and active evidence accumulation, what emerges as important neuronal correlates are things like the N2 or the P300 or the P3, which is, of course, one thing that you could choose to put into the universal function approximator. So, just knowing that these are important, and principled data features, observable things that report exactly the kind of sense-making, belief updating, active inference that you are interested in, may be a useful justification for why you're using these as opposed to something else. So I thought that might be useful for you. I'm trying to another example of this kind of simulation can be found in terms of solving rules. I can't remember the specific reason I put this up, but this may or may not be of interest in terms of trying to maximize, reduce uncertainty by actively looking at different parts of a screen. I just wonder if we got that's a shame. Active curiosity in this, no. My apologies, I've got too much up here. Right, but this it's a shame I can't show you the. So this was actually had a very similar setup to some of your paradigms, where you have to report the correct color by looking at a triad of different colored circles, and then simulating which circle or which part of the screen should I look at next in order to resolve uncertainty about what is the correct color, and furthermore, what is the rule that is underneath that. So that may or may not be of interest. This paper I thought you might be potentially interested in, because what it does is it uses these kinds of models to model a saccadic cancellation task. So in neurology, you sometimes come across conditions where people effectively ignore one half of the visual field. So this would be basically they're not able to attend to the left half, for example, of the graphics, and they don't know that. And the way that you assess that is to have something called a line cancellation task. So basically, you ask the subject, you present them with a whole set of dots in the visual scene, and you ask them to draw a line through all the ones that they can see. And what typically happens with these patients is that they fail to cancel the dots that they cannot see or attend to. So this struck me as being, if you like, the clinical homologue of the kind of visual foraging that you're talking about, in the sense that you are testing, you want to optimize the ability of subjects to immediately identify where is the salient information and then report where that information is. And in this instance, the reporting was actually through saccadic eye movements where they actually looked, which you can measure with your eye tracking. And you can also model, in this particular example, the modeling was more in the service of trying to understand the failure of cancelling in neglect syndrome. So this was not so much how to optimize the visual foraging or the epistemic foraging, but how to explain the failure of this kind of foraging for information in the context of neurological conditions that have this, which are called neglect syndrome. So that was by Thomas Parr, the computational anatomy of visual neglect, which might be, again, something else you might want to refer to. I put this paper up because you can actually use the same kind of models, Markov decision process models. This is pupillary. You can use the same kind of models to simulate changes in heart rate depending upon what you're looking. So there was, I thought, a really interesting part of your presentation where you were talking about the consequences for your physiological arousal, your autonomic arousal, given in the face of irreducible uncertainty. So you're overwhelmed, you don't know where to look next, and you can't resolve any uncertainty, and you may get aroused. But of course, there was also the reciprocal causal direction. When you are aroused, you are changing the way that you sample data. So, for example, every heartbeat compromises visual retinal detection by engorging the retina. So, this might be one interesting avenue to pursue, to actually synchronize the visual display with the subject's heartbeat in a way that eludes those parts of the cardiac cycle where you are effectively blind. And you can simulate this by basically having a Markov decision process or hidden Markov model that renders the visual sampling of a scene dependent upon the cardiac phase, and you can demonstrate the consequences of that, which is effectively simulated heart rate responses and invoked, I think, simulated ECG traces. Again, that you could, in principle, then fit to actual real ECG changes, or in the shorter term, just say that this is why we were measuring heart rate variability or heart rates, for example, because we now have a formal understanding that this is intimately related to visual foraging and the resolution of uncertainty and arousal. Well, there's a hand up. I'll stop talking for a second.
Sorry, I have a question. Okay, so what I pursue here as with the computational modeling perspective, like suppose consider if a system is, example, if you consider a single neuron model, Hush model, right? So from the output responses of a single neuron, we know this is going to be the action potential, we are going to get it. So those things will be described with the difference and differential equations. So now here the point is, how are we going to synthesize the inter-subject variability as well as intra-subject variability? Example, you have a Hush model for the single neurons. Suppose if a group of neurons is going to make a behavioral responses, right? So in this case, so our ultimate goal here for our study is, so we need to check out how the firing is going to happen. So we need to model that aspect from the user.
Yep.
So that's what we are trying to find out the way to generate the data in our applications. Even with the, if you look at with the simple cardiac model, like we have 10-2 model and we have some other model to make a cardiac muscle level modeling, right? So here, if we consider a system as an individual entity, also we can describe from the responses of the system, we can easily describe that one with the computation model with either with the normal theoretical differential equations or with the existing application, what you have suggested so far. So how are we going to model these interdependencies across the system? Example, so here the user responses, it depends on several parameters. So we need to model the inter-subject as well as subject variability. So which way we can address that? Could you please emphasize that point? Because that will be useful for us to make a data generation?
Yeah. If you wanted to do that, well, first of all, let me just answer the question: how do you relate this kind of formal evidence accumulation scheme to neuronal dynamics? You do it by basically doing a gradient flow on a in machine learning, what would be called an elbow, an evidence lower bound. In active inference, it would be called variational free energy, so that the neural dynamics are simply the gradient or gradient descent optimization of these bounds on the marginal likelihood or the model evidence for a particular input. In relation to your question, how would you personalize any given model of any given task for this particular subject? Then that generative model, as you say, has a number of parameters that are read as priors on the model, and then you using a separate optimization scheme optimize the priors, the parameters of the priors, until either the behavioral responses or the physiological responses best explain that particular subject's responses. So that's how you would model the intersubject variability, and that's what I meant by computational phenotyping. So you take this kind of subject or that kind of subject, and then.
Sorry for the interruption. So we have already like experienced some more model like a cancer, mainly for the EEG applications. So here my concern is, suppose consider we have a different visualization, we have got the responses, right? So I need to generalize the model. Example, we have a visual primitives, we have a square, we have a color, we have a line with thickness, line with colors. So for the individual adaptations, we have an unique EEG responses. Right. So now suppose I can't generalize the model for all these things, because suppose consider a person is already in a partial adaptation. So now we are going to introduce one more adaptation to make the user to get benefited. So in that case, we have to make a data generation. So what do you suggest? For each adaptation, we have to generate a different, make a different generative models, or a single model is capable of generating all the kind of data. So whereas here we have only less data in our hand, we can't describe this data responses in terms of we can't suppose consider if it is single evoked potential, we can know how the waveform pattern will be. So it's a series of evoked potential. That evoked potential might be steady state. Also it ran more non-stationarity. So this is what the difficulties we are facing in data generation in our applications. So how can we tackle this issue in this use case? Yes.
Right. Well, what I'm proposing here is really motivating the particular choices that you've already made, and giving you examples that these particular data features you've already identified are informative about the generic process of visual foraging to reduce uncertainty, getting as much information as quickly as possible from a visual scene, for you, a video screen, into some belief structure in a brain. So a lot of these responses will not be specific to whether it's changing the color or whether it's the responses to changes in the format. This is more a reflection of the process of evidence accumulation and its convergence, and demonstrating that these kinds of responses are indeed tapping into the kind of measures that you've got empirically for each of the subjects. But the whole point of, so the way that one usually deploys this kind of computational phenotyping is to take a standard paradigm, sometimes a game theoretic paradigm, but for you it could be the first instance of that you illustrated with changing from bar charts to going from the difference between the responses to information about gender in terms of E and F to colors, colored circles, for example. So keep the paradigm really simple, and then just simulate that. And then the generic difference between an easy and a overwhelming, or between the kind of stimuli that this subject finds easy and finds overwhelming, and or more compact and easier to forage, will then tell you tell you or enable you to use this standard paradigm to quantify the hyperparameters and the precisions of this generative model, of this very simple paradigm. So you use standardized tasks to phenotype. So this is usually in the psychiatric context, where somebody may have, say, addiction or not be addicted. So what's the difference in the way that they make their decisions that makes them more into an addictive person or other person? And the way that one does it is by committing to a particular task paradigm, a very simple one, and then phenotyping, so that you're now identifying what part of their computational architecture distinguishes between people who are addictive versus not addictive. So this is not a model of all the particular use cases that you might want to deploy. What it does is it validates the use of these signatures, these data features that are reflecting key differences between subjects that are pertinent to this kind of behavior or decision making. Does that make sense?
Yeah, I have one more point I need to get clarified. Suppose consider there are some behavioral responses has some quasi-sinusoidal pattern in it. Okay, for generating those kind of patterns or impulse like structure, even the action potential like structure, okay, it's fine. But whereas in EEG cases, right, suppose I'm gonna generate a data sequence from the generative model. We know, right, it's like a kind of a white noise sequences, right? So even if one sample shift, if I take an autocorrelation measure, it's giving me 0. So I couldn't even quantify whether the generated data is actually belongs to the right context or not. So that's also one of the challenges what we are facing over here. So
Right,
how
so
can I address this? Yes.
Are you asking how can I motivate choosing the right kinds of data features based upon my EEG? Is that and right? Well, that's exactly why I'm hoping this might be useful. So for a start, well, not this particular one, but right. Well, no, that's although actually no, this is well. Why I was showing you the simulated mismatch negativity and P300 responses before. So that would immediately say, right, what I want to do now is, as part of my data feature selection, I'm going to choose event-related potentials that are averages of single kinds of trials, and you can do your trial, your trial-based averaging according to the experimental design. That would be one important data feature. I notice you're not using that. You're using spectral analysis. So in EEG data feature selection, you can go one of two ways. You can either do event-related responses, where you're plotting the average as a function of some peristimulus time locked to a particular event, say, for example, a saccadic eye movement, or some change in the screen, for example. Or you can do induced responses, and induced responses basically mean I'm now not taking the power of the average response over certain events, but the average power over time, and then that allows you to decompose into different frequency bands. That's a different kind of data feature. Is it relevant for these event-based approaches? No. Is it relevant for various states of mind? Yes, possibly. And that was we've done this one, so we can get rid of this in the body's eye. And that was just the same thing. Good. Okay. And that was the good. We can get rid of that one as well. That was the reason I put this paper up. So there's quite a lot of literature on the spectral asymmetries implied by the neuronal dynamics that we were just talking about. So this is a complementary approach that doesn't look at the event-related responses, for example, a P300 or an N2 or a particular waveform of a peristimulus time function or function of peristimulus time response, but looks at the spectral asymmetries. So similar to your theta over alpha ratio or your lateralization ratio of, say, alpha power. But in this instance, it was specifically looking at asymmetries in terms of bottom-up and top-down processing from the visual cortex, which may be relevant from your point of view, because this was being looking at the differences in the spectral profiles of neuronal message passing of the kind implied by this belief updating or evidence accumulation under different attentional sets. So when, in this instance, these were monkeys, thought it was important to attend to this patch of the visual scene as opposed to that patch. Could one demonstrate, in fact, this, this is actually even an earlier paper and addressed an even simpler question about the differences in forward and backward frequencies. So this is an example of, should you want to, motivating the spectral asymmetry indices. My apologies, my fire is making a strange noise. In term and trying to understand differences or the asymmetries in different frequency bands when looking at spectral responses in higher and lower. So it's not right versus left, but this is particular levels in the visual hierarchy. Again, I'm not saying that you should do this. What I'm saying is that you're fully licensed to use spectral data features, which would be the summary of ongoing activity, as something that may usefully be reporting this kind of evidence assimilation. In this particular example, the theoretical motivation was not from evidence accumulation with discrete sort of Markov decision processes and discrete eye movements, but more a predictive coding formulation, which you can also read if you do as Kalman filtering or Kalman-Busey filtering. So this would be an example of saying, it may be important to look at the relative power in different frequency bands, particularly looking at the ratio of high and low. So you were, in your instance, it would have been alpha and theta. In this particular example, it was more the difference between sort of lower frequencies in the theta band and faster gamma frequencies, which you might also want to think about in terms of different kinds of data features. Yeah.
Yeah. So I have one question. Suppose consider for our study, we have a behavioral data. So we have taken the alpha theta ratio between the frontal and the parietal region to measure the internal and external attentions. Because mostly the study is about mental state prediction based on the internal and external attention. So internal attentions, they are remembering, okay, what are the visual primitives and associated informations. Sometimes the information is presented, they are doing some visual search. So whereas also one more thing we have observed that, so in terms of event-related activity evoked in the 6 layers of visual cortex in the human brain, so we couldn't even find the distinction between color stimulus versus the baseline stimulus. The activation was too low, so that is the reason in this mainly in this application. So mostly it's attention specific and memory specific. We went with the frontal and parietal region. So that's what we got the more spontaneous as well as coherent activations in the topograph. So now here major my concern is, as I stated earlier, if you generate a synthetic data, even with the behavior, the first question is about intersubject as well as intrasubject variability. How are we going to address in both EEG as well as eye gaze information? Also, one more point here is for the same visualization, example, for image one, we have a certain type of questions. With the question, we can able to trace, okay, these are all the visual trajectories as well as the fixation saccade points the person has seen. That information we can get it, so that is more deterministic. Okay, in that aspect, modeling will be helpful. So mostly my major concern is and informations. So here in terms of generation, how are you gonna validate that information with the neurophysiological modeling? That's the question. So also as I suggested, so even the input space we need to explore. Like here with right now I got a point with the ET metric you mentioned about different scan path, even with the saccade durations, that is gonna help us to get wider input space. So that part was clear. With even with the EEG matrix, we are not sure whether we can get also like a continuous space. So where finally we can map function should be one to one, right? Mostly. So one to many is not possible in terms of functions.
Right. Yeah, I mean, I tend to agree with you. I think the sort of spectral responses are probably not the most efficient data features. I would have gone for event-related responses, time locked to saccades or time locked to changes in the visual stimulus. The spectral responses, as you pointed out, are more useful in comparing what's known in my world as attentional set. So I was imagining that your cognitive state in a simple mind could be under a state of uncertainty and arousal with a particular attentional set, as opposed to having sort of focused attention, having identified exactly what you should be looking at. So those more contextual cognitive states, as opposed to fast fluctuations in belief states associated with event-related or evoked components, can be captured by the spectral densities. But you're absolutely right. It doesn't surprise me in the slightest to hear that you couldn't get any spectral differences between coloured and black and white. But you could, get a difference between, tasks in which it is impossible to know where to look next, and tasks where it's easy to know where to look next. And you would imagine that to be more expressed in terms of the spectral density. So, I'm not saying that this is the best data feature. I'm just saying, should you want to use spectral data features, then there is an excuse for you to use them. In answer to your question, how do you estimate the parameters in this instance of the subject-specific process generating these spectral data features? That, in my world, would be achieved using dynamic causal modeling. So you basically set up a state space model, and then you infer, or estimate the parameters of that state space model that happens to be a neural mass model in exactly the way that you were articulating, with differential equations that are plausible for population responses, and then you estimate. Then you can estimate them. You could certainly do this, and that's one way of, if you like, summarizing. Perhaps it speaks to one of the challenges, in terms of operationalizing the signals. There's a procedure in the neurosciences called generative embedding, and what that basically means is you take some EEG time series, and then instead of abstracting some data features like the spectral profiles or asymmetries or ratios, or indeed event-related potentials, you fit a neural mass model with multiple sources, can be quite a deep model, to either the ERP data or the induced responses, the continuous spectral profile. In fact, it uses a complex cross spectrum, so you have the delays in. So that now you're summarizing either event-related responses or induced responses over time in terms of a small number of synaptic parameters that are parameters of the neural masses, and then that becomes your new data feature. So that's one way of compressing a high-dimensional neurophysiological data into a smaller number of parameters and into a smaller number of space that then usually has a better predictive validity when you then apply some classification or machine learning to this condensed or embedded parameterization or summary of the data. Again, I don't think you have time to do this, but certainly you could suggest that this kind of approach is available, and interestingly has been applied to the neurophysiological features that you're using in their raw terms at the moment to characterize or fingerprint or phenotype physiologically this particular subject in this particular cognitive state. And then just finally, you were talking a lot about I think it was I can't remember the acronym, but it looked like galvanic skin responses. One really useful measure, which in principle you should have if you've got the eye tracking, is pupil diameter, and that's really useful because that's much faster than the galvanic skin responses, but also can be read as a direct report of the encoding of uncertainty in terms of certain modulatory neurotransmitters such as adrenaline and, well, in fact, specifically in terms of adrenaline when it comes to uncertainty. So this is an example of many papers, but useful in terms of specifically how pupillary dilatation can report the uncertainty that's been inferred when foraging in this visual scene. So again, you might expect that there would be systematic differences in pupil diameter between complex and simple scenes, but as you were able to sort of forage and focus down on a complex scene on what you thought was salient or had a high expected information gain, you should get systematic changes in pupillary responses. Not illustrated here, unfortunately. Oh, perhaps they're underneath. Oh, yeah. Just showing how to infit empirical pupillary dilatation using a model based upon the same tasks that the subjects were asked to do. So this is not a data feature or type that you brought to the table. But it would be one which might be naturally included in your basket of physiological measures, and I would recommend that over heart rate variability, although that was only implicit in your presentation, and galvanic skin responses. It's just a tighter, it's more closely related to arousal from the point of view of the central nervous system, and it has a faster response profile. It's still slightly sluggish, but it's not as sluggish as your galvanic skin responses.
Carl, I think we have overexceeded the time you allocated for us today, and I feel kind of bad because it looks like it's night there, and we took more of your time than we expected. I don't know. Is this maybe a good point to wrap it up, or?
Yeah, but please don't worry. I enjoy doing this. It's,
Okay.
keeps me young and awake.
Okay, perfect. I mean, if I may jump in, you gave us a lot of options, and I'll do the devil's advocate here. You pointed out on several occasions that you're not advising us to necessarily follow that approach, but either use it also as evidence or try something at early stage, and to motivate the solution. And I'm just trying to think, if that would be a viable option for us when we, meet the reviewers the next time, to say, there is a bunch of work there that suggests this can be operationalized X, Y, Z, and we have some preliminary evidence. And that's great. What I'm concerned is that our time is kind of running out, and I wish we had ample time to explore these options, because I mean, personally, I'm a big fan of the work you've done on active inference, and all these papers are like great ideas. I would really like to try them out in the lab and see how we can put them in practice. So just, for the sake of asking, do you think the approach of us using the data we've collected and we are going to collect in the next weeks as a kind of basis to synthesize some additional data, adding some noise on that, try to map basically the visual stimuli to the ERPs or some kind of representation of the signals we are collecting using diffusion models or generative models? Do you think that would be like a really bad idea? Because from what we discussed, I think that could be another way to scale up the data on top of what you suggested with Markov decision process model, or other ways we could create some kind of surrogate model of the human user, which I really like as an idea.
Yes, no,
Or have you experienced, have you done something like that in the past? You maybe have some other work. I mean, for example, since you pointed out some papers, there is a paper we found, although we haven't read it. We were just doing a quick review, a quick search now, and we run. I'm not sure if I can type something. There is no chat option.
I think yes. I think you have to
Yeah,
be.
there's a chat.
There is a chat.
I know it's not working. So
no,
you can see your screen maybe.
Yes.
Yeah, definitely. Something something like along these lines, where we have this data augmentation, data synthesis solutions. Do you see that as a really bad idea? Or, because just to weigh our options in the next days, we have to discuss, probably go over today's session again and watch it again and see what's realistic. Go over the papers you suggested, but at the end of the day, I think we will probably have one chance at doing this, and I'm not sure.
Yes.
What would be our best bet?
Well, I mean, strategically, what I had in mind, I didn't realize you still had to answer to reviewers. I assumed you got the money. And
we do every year.
Oh, really? Oh dear. Well, okay. So I get the impression that you have laid out your road and you have to pursue that, and that you are going to be using machine learning to use all these really informative proxies for the cognitive state, reflecting the efficiency of this epistemic foraging as a function of how easy it is and the scheduling of that. So under that remit, all I was doing was just providing you with moral defenses of why you've chosen the particular data features, because it hasn't come out of thin air. You can say, oh no, we've looked at the literature and we've spoken to people like Professor Friston, and he said, yes, those are exactly the right data features to use. Actually, he also pointed out pupillary dilatation, which we hadn't actually put in, but now we will. And this is why, if you want to know why, just go and look at this theoretical work. We don't need to pursue this. We just need the good data. And if we now have the right data, and certainly we've got sort of canonical data from our experimental subjects and our proof of principle, which we can now just equip with random fluctuations and use as surrogate data to get robust machine learning, noting that, of course, you will, for free, elude all the sharp minima and the overfitting, because you're adding the right amount of noise to these canonical data. So I think that'd be perfectly plausible. You could even find a literature, and I remember reviewing papers on DeepRL, showing you get better generalization performance when you add the noise, because there's a particular problem with most machine learning approaches that they tend to get trapped in local minima, and those minima are too sharp because you're not modeling the uncertainty. So one way to elude these local minima, getting trapped in local sharp minima, is just to keep on mini batching, but mini batching with extra noise, and that tends to sort of smooth things out a little bit. So I think that'd be perfectly plausible. So all I've said today is really just to give you a narrative to impress reviewers about what could be done or why you have done what you have done so far. So that's I don't think if you wanted to do any of these things, the dynamic causal modeling, the generative embedding, the simulation of visual searches, those would be that would be another program of work. And very, very interesting, but it would take you 1-2 years to do any of those. So I was really endorsing your strategic. You can use what I've said as moral support for what you will be doing in the next few days or weeks or months.
I mean that makes sense. I mean, we were definitely actually counting on your feedback to see if any of the ideas you'll give us today could be used to support, let's say, some of the action items we have in mind implementing in the next weeks, months. Definitely, it will help us build a narrative. It's very difficult. I mean, with review panels, especially yearly ones, it's tricky. You need to, beyond a strong narrative, you need to at some point show some kind of evidence, and we have some evidence. We have partial evidence, but we're at the point where now we need to connect this with machine learning algorithms, and that's the biggest challenge, I guess. But I think you gave us enough material, enough ideas to consider, and in the next days I would say watch this discussion, this video again, and have another brainstorming amongst ourselves and see what and go over the papers you shared and determine what would be the best approach. So I guess I think if nobody objects, maybe we can thank you again for giving us this great opportunity, this amazing opportunity. First of all, get to know you a bit. I've heard only nice things about you from Zafiris, whom I met last time I visited London, and maybe in one of the next visits I'll ping you and maybe arrange a visit, meet you in person. That would be really, really amazing. And thanks to Miguel for organizing this and everybody who attended. And I guess thanks everyone for joining today. We can.
Miguel will make us clap you now. So
yeah, we usually make a final round of applause to everyone. So everyone, thank you everyone for attending.
Thank you.
Thank you for your presentation, and thank you, Carl, for your.
I think this is the point where we unmute and clap, right?
Yeah.
Don't clap while muted.
Yeah. Thank you, everyone. See you in the next one.
Thank you.
Bye.
Bye.